In the previous chapters, we established the fundamentals of petroleum production and introduced the overall production system. Now, we turn our attention to the reservoir, the source of all hydrocarbon production. This chapter explains how fluids flow from the reservoir into the wellbore by examining the relationship between reservoir pressure, flowing bottomhole pressure, and production rate. By the end of this chapter, you will be able to evaluate inflow performance and understand the principles behind Inflow Performance Relationship, IPR, analysis. In this chapter, we'll study the reservoir system and learn how to evaluate the inflow performance of oil wells. The objective of this chapter is to understand how fluids flow from the reservoir into the wellbore and how reservoir pressure, bottomhole flowing pressure, and well properties control production rate. We'll begin with the productivity index, or PI, which describes single-phase flow above the bubble point pressure. We'll then examine Vogel's method for two-phase flow, followed by the Composite IPR approach that combines both methods when the flowing pressure falls below the bubble point. Next, we'll investigate the effects of skin factor and flow efficiency on well productivity, learn how to construct and interpret Inflow Performance Relationship, or IPR, curves, and solve practical engineering examples. Finally, we'll explore methods for predicting future well performance and discuss how these techniques are applied in the field. A companion interactive dashboard is available on request. It allows you to modify key parameters and instantly observe their effects on reservoir performance and inflow behavior. A 3-minute tutorial video is included to demonstrate how to use the dashboard. If you would like access, please contact me. By the end of this chapter, you'll be able to select the appropriate IPR method for different reservoir conditions, calculate well deliverability, interpret IPR curves, and understand how reservoir properties influence production performance. These concepts form the foundation of production engineering and are widely used in reservoir evaluation, well testing, production optimization, and field development. Imagine two wells producing from the same reservoir. One produces twice as much oil as the other, even though both experience the same pressure drop. Why? The answer is the productivity index, or PI. PI tells us how efficiently a reservoir delivers fluids to the wellbore. A high PI means the reservoir has excellent flow capacity. A low PI often indicates poor permeability, formation damage, or flow restrictions. One important limitation is that PI only applies when the reservoir pressure remains above the bubble point. In this region, only liquid flows, and production increases linearly with pressure drawdown. Think of PI as the reservoir's productivity score. It provides the foundation for understanding well performance and constructing Inflow Performance Relationship, or IPR, curves. A common mistake is to assume that one equation can predict the performance of every well. It cannot, because reservoirs change as pressure declines. When the reservoir pressure remains above the bubble point, only liquid flows through the reservoir. The relationship between pressure and production rate is almost perfectly linear, making the productivity index, or PI, method the correct choice. As the pressure drops below the bubble point, dissolved gas starts coming out of the oil. The reservoir now contains both oil and free gas, causing the flow behavior to become nonlinear. This is why Vogel's equation provides a much more accurate prediction. Many wells experience both conditions during their productive life. They begin with single-phase flow and later transition to two-phase flow. In these cases, the Composite IPR method combines both models to represent the complete inflow behavior. The lesson is simple. Before calculating production, identify the reservoir condition first. Choosing the wrong IPR model can lead to large errors in production forecasts, reserve estimates, and development decisions. Let's build an IPR curve together. Imagine you've just received data from a newly tested well. Where do you start? First, collect the 3 most important measurements: reservoir pressure, flowing bottomhole pressure, and production rate. Think of these as the vital signs of the well. Now ask yourself the first engineering question: is the reservoir pressure above or below the bubble point? Your answer determines which IPR model you should use. Above the bubble point? Use the PI method. Below it? Use Vogel's equation. If the reservoir spans both conditions, use the Composite IPR method. Let's take a simple example. Suppose the reservoir pressure is 3000 psi, the flowing bottomhole pressure is 2000 psi, and the well produces 1000 stb per day. From these values, you can calculate the productivity index and then predict the production rate at many different bottomhole pressures. Instead of calculating just one point, Repeat the calculation for several pressures, such as 2800, 2500, 2000, 1500, 1000, and 500 psi. Each calculation gives another point. Connect all the points, and the complete IPR curve appears. Now comes the engineering insight. What happens if we lower the bottom hole pressure? Production increases. What if the reservoir pressure declines over time? The entire IPR curve shifts downward, and the well delivers less fluid. This is exactly where the companion interactive dashboard becomes valuable. You can change reservoir pressure, flowing bottom hole pressure, productivity index, bubble point, and other parameters, then instantly watch the IPR curve change. Within minutes, you'll develop an intuitive understanding that would otherwise require solving dozens of calculations by hand. Here's an interesting question. If two wells are both producing 1,000 barrels of oil per day, are they performing equally well? The answer is not necessarily. Imagine well A and well B each produce 1,000 STB a day. At first glance, they look identical. But when we compare each well to its theoretical maximum production, a different story emerges. Suppose well A could ideally produce 1,020 STB a day. Its flow efficiency is about 98%, meaning the well is performing very close to its full potential. Now consider well B. If its theoretical maximum is 1,500 STB a day, then producing 1,000 STB a day gives a flow efficiency of only 67%. Although its production rate is the same as well A, this well has lost a significant amount of productivity. So what causes this loss? Common reasons include formation damage, positive skin, scale buildup, or an inefficient completion that restricts flow into the wellbore. Now here's the opposite situation. After a successful acidizing or hydraulic fracturing treatment, a well may produce even better than its original undamaged condition. In that case, the flow efficiency can exceed 100%, indicating that the stimulation has improved the reservoir's ability to deliver fluids. So ask yourself, is the well producing as much as it can, or just as much as it happens to be producing? That is the question flow efficiency answers. It tells engineers, in a single number, whether a well is healthy, damaged, or has been successfully stimulated, making it one of the fastest and most powerful diagnostic tools in production engineering. Let's imagine two wells drilled into the same reservoir, with the same reservoir pressure, the same rock properties, and the same completion design. Should they produce the same amount? You might expect the answer to be yes, but in practice, they often don't. The reason is frequently skin factor. Think of skin as the condition of the rock immediately surrounding the wellbore, the final pathway that every drop of fluid must pass through before entering the well. If this zone becomes damaged by drilling mud, fines migration, or scale deposition, it creates extra resistance to flow. This is called positive skin, and it reduces production because the reservoir must lose more pressure to push fluids into the well. Now imagine the opposite. After an acidizing or hydraulic fracturing treatment, the flow path becomes easier than before. This produces negative skin, allowing fluids to enter the well with less resistance and increasing production. A skin factor of 0 represents the ideal case, where the well neither restricts nor enhances flow. Here's a challenge. Open the companion dashboard and change only the skin factor while keeping every other parameter the same. Watch how the IPR curve shifts. You'll discover that changing a single number, from +5 to -3, can transform an average producer into an excellent one, or turn a high-performing well into a disappointing producer. That's why skin factor is one of the first parameters production engineers evaluate when diagnosing well performance. When engineers calculate a skin factor of +8, the next question isn't how do we remove it. The first question is what is causing it. Skin is rarely the result of a single problem. Think of it as the sum of several flow restrictions, each adding its own resistance around the wellbore. For example, formation damage from drilling fluids may plug the pore spaces and reduce permeability. Partial completion means only part of the reservoir is open to flow, forcing fluids to squeeze through a smaller interval. Water or gas coning disturbs the flow pattern and creates additional pressure losses. Even poor perforation design, such as too few perforations or shallow penetration, can significantly restrict inflow. Here's an example. Suppose a well has a total skin of +8. Detailed analysis shows that +5 comes from formation damage, +2 from poor perforations, and +1 from partial completion. If you only reperforate the well, the skin falls from +8 to +6, and the improvement is small. But if you remove the formation damage through a successful stimulation treatment, the skin drops to +3, producing a much larger increase in production. This is why diagnosis comes before treatment. The goal is not simply to reduce skin. The goal is to identify the largest contributor and eliminate it first. Smart engineers solve the real problem, not just the visible symptom. Let's walk through a real field example. An appraisal well is drilled in a newly discovered reservoir. During drilling, no mud acid treatment is performed, so there is a possibility that drilling fluids have damaged the formation near the wellbore. The well is completed and a production test is carried out. The result is disappointing. Oil either does not flow, or the production rate is much lower than expected. The operations team quickly suggests, let's acidize the well. But as production engineers collaborating with the reservoir engineers, we don't make decisions based on assumptions. We collect evidence first. The first step is to perform a pressure buildup test. After shutting the well in, we monitor how the pressure recovers with time. This test tells us far more than the production rate alone. From the buildup analysis, we estimate the formation permeability, average reservoir pressure, and most importantly, the skin factor. Now we begin to understand why the well is underperforming. Next, we use the test results to construct the Inflow Performance Relationship, IPR. This tells us how much the well should produce under different flowing bottomhole pressures and allows us to compare the actual well with its theoretical performance. Now comes the key engineering question. What is causing the skin? Suppose the buildup analysis gives a skin of +10. Does that automatically justify acidizing? No. Skin is only a number. We must determine whether it is removable. If the positive skin is caused by mud invasion or formation damage, acidizing may reduce the skin from +10 to +2, significantly increasing production. But suppose the buildup test also indicates extremely low permeability, a thin productive interval, or evidence of boundary effects. In that case, the poor performance is controlled by the reservoir itself, not by removable damage. Even after acidizing, production may improve very little because the real limitation remains. This is why well testing is the foundation of every stimulation decision. The buildup test doesn't simply calculate skin. It tells us whether the reservoir can respond to stimulation. Never acidize because the well is producing poorly. Acidize only when pressure transient analysis shows that the production loss is caused by removable near wellbore damage. Remember this principle. Production testing tells you what the well is doing. Pressure buildup testing tells you why it is doing it. Good engineers do not ask, can we stimulate the well? They ask, will stimulation remove the real cause of the problem? That single question can save a company millions of dollars and prevent unnecessary interventions. Diagnosis always comes before treatment. Imagine drilling a well into an excellent reservoir with high porosity, good permeability, and plenty of oil. Everything looks promising. Yet when the well is tested, production is far below expectations. What happened? In many cases, the reservoir is not the problem. We damaged it ourselves. Formation damage can begin the moment the drill bit enters the reservoir. Drilling mud may invade the formation and plug pore spaces. During completion, fines can migrate and block flow channels. As production continues, mineral scale, wax, or incompatible fluids may further restrict the pathways that oil must travel to reach the wellbore. Even an improperly designed stimulation treatment can create additional damage instead of improving the well. Think of the reservoir as a multi-lane highway carrying oil toward the well. Formation damage is like closing lane after lane. The oil is still there, but traffic slows dramatically because fewer pathways remain open. Can we always fix formation damage? No. That is one of the biggest misconceptions in petroleum engineering. Some damage is reversible, while some is permanent. If the damage is caused by mud solids, mineral scale, or certain precipitates, treatments such as acidizing or solvent cleaning may restore much of the lost permeability. However, if the rock fabric has been permanently altered by severe clay swelling, pore collapse, or irreversible fines migration, stimulation may provide little or no improvement. This is why engineers never prescribe acidizing simply because a well has a high skin factor or low production. First, they perform pressure transient testing, analyze the buildup data, estimate the skin, review drilling and completion history, and identify the actual damage mechanism. Remember this principle. A well does not need treatment because it has low production. A well needs treatment only when the cause of that low production is understood and can be removed. The best production engineers don't ask, "How do we stimulate this well?" They ask, "What is preventing this reservoir from delivering its full potential?" Once that question is answered, the right solution often becomes obvious. Here's a question every petroleum engineer should ask. If this well is producing well today, will it still be producing well 5 years from now? The answer is probably not, because a reservoir is a dynamic system. Every barrel of oil or cubic meter of gas produced removes energy from the reservoir. As reservoir pressure declines, the well gradually loses its ability to deliver fluids to the surface. Think of the IPR curve as a snapshot in time. It describes the well's inflow performance today. But 6 months, 2 years, or 5 years later, that curve may no longer be valid because the reservoir has changed. Let's consider an example. Today, the reservoir pressure is 4,000 psi, and the well can produce 2,500 stb a day. After several years of production, the pressure declines to 3,000 psi. Without changing the well completion or surface facilities, the maximum production rate may fall to 1,700 stb a day. Nothing has gone wrong with the well. The reservoir simply has less energy to drive the fluids. By forecasting future reservoir pressure, engineers can generate future IPR curves and visualize how the well's performance will evolve throughout its life. Instead of reacting after production declines, they can prepare in advance. Ask yourself, when should artificial lift be installed? When is the best time to acidize the well? When will a workover become economically justified? Should new infill wells be drilled? These questions are answered not by today's IPR curve, but by tomorrow's. This is why future IPR prediction is one of the most valuable planning tools in reservoir engineering. It transforms production forecasting into decision forecasting, allowing engineers to optimize investments, reduce surprises, and maximize recovery over the entire life of the field. Remember, the goal is not to predict the future perfectly. The goal is to be prepared for it before it arrives. Before you calculate a single production rate or draw your first IPR curve, ask yourself one simple question. What is driving the reservoir? This is one of the most important questions in production engineering because the same well can behave very differently depending on where its energy comes from. Think of the reservoir as a battery. Every well needs energy to push fluids toward the wellbore. The question is, where is that energy coming from? Is it a strong aquifer continuously pushing water into the reservoir and maintaining pressure? Is it gas expanding from a gas cap? Is it dissolved gas coming out of the oil as pressure declines? Or is the reservoir simply depleting, losing pressure with every barrel produced? Consider two reservoirs that are identical in size, porosity, permeability, and even initial pressure. One is supported by a strong water drive, while the other is a depletion drive reservoir. After producing the same amount of oil, the water drive reservoir may lose very little pressure and continue delivering high production rates. The depletion drive reservoir, however, may experience a rapid pressure decline, causing its IPR curve to shift downward much sooner. Now ask yourself, should both reservoirs be analyzed using the same assumptions? Of course not. Their behavior is fundamentally different because their energy sources are different. This is why experienced engineers study the reservoir before selecting the equation. The drive mechanism tells you how reservoir pressure will evolve, how production will decline, and which IPR model is most appropriate. Remember this principle. Equations do not choose themselves. The reservoir chooses the equation. When you understand how the reservoir generates and maintains its energy, selecting the correct IPR method becomes an engineering decision based on physics, not guesswork. This chapter is accompanied by an interactive dashboard that allows you to explore IPR analysis in real time. Adjust reservoir and well parameters, visualize PI, Vogel, and Composite IPR curves, and follow the step-by-step engineering calculations used throughout the lecture. It is designed to reinforce the concepts presented in this chapter through hands-on learning and immediate visual feedback. Interested in using the dashboard for teaching, training, or professional applications? Feel free to contact me for access and further information.